Deterministic finite automata, or DFAs, are computational models with limited memory or no memory at all. A real-world example of such a DFA would be like the light in your fridge. It has two states, on and off, and those states are determined by the door being open or closed. We can create a special picture called a state diagram to represent this machine. The arrow coming in from the left points us to our starting state, off. Then, as we feed inputs to each state, we can transition from the off state to the on state and vice versa. Let's go ahead and take a look at another general example. This DFA will have three states that we will call Q1, Q2, and Q3. The arrow coming in from nowhere on the left marks our starting state, where we begin computation. The state with two circles is called the accept state, and this is where our machine can consider a computation as complete and an input as valid. Arrows from one state to another are called transitions, and the inputs marked above them are what trigger the state change. We can feed this machine strings of zeros and ones, and it will read them left to right. For example, let's give it the string 10001. We start in Q1, we read the first one and go to state 2. Then, we read a 0 and go to state 3. We read another 0 and go to state 2. Then, we read one more 0 and go to state 3. Then, we read the final character 1 and move to state 2. We have ended at the accept state, so we can consider this input as valid and our computation complete. What we have created, while useful, is informal. The formal definition of a DFA is a tuple of 5 elements. The first is Q, which is a finite set of states. The second is a finite set called the alphabet of the machine. This represents the characters that an input string can contain. We used zeros and ones for our example above. Third is the transition function. For each state, we need to define the behavior for each possible input at that state. This is written as the cross product between our alphabet and our set of states. Using our example machine above, the delta for state 1 looks like this. The inputs to the function are our current state and the input, and the output is the destination state. Fourth is Q0, which is the start state. There can only be one. And the last element of the tuple is F, which is the set of accept states. We can have multiple accept states. Let's define our last example machine using this formal definition. Q, the set of states, is Q1, Q2, and Q3. The alphabet of our machine is the set of 0 and 1. Our transition function will look like this. The start state, Q0, is marked as Q1. And our set of accept states only has one state, which is Q2. If we take this formal definition and we can generalize all the input strings that a machine accepts, we call those inputs the language of the machine. For our example machine, the language would be a set of strings, where each string contains at least one 1 and an even number of zeros that appear after the last 1. Let's take another look at one more fun example. If we draw this machine, we notice that branching occurs. The first transition we make determines which branch of the machine we take. One side ends in ones, and the other ends in zeros. The language of this machine are inputs that start and end with the same character. Now that we have formalized the definition of finite automata, let's formalize the definition of computation for finite automata. Computation is the process that occurs when we feed some machine M a string W. This string has to be made up of the machine's alphabet. We say that M accepts W, or put differently, W belongs to the language of M if a sequence of states exist within the machine that have the following conditions. Condition 1 just means that the machine starts in the start state for a given input. Condition 2 means that for each piece of the input, we move from our current state to the next state in a way that is defined by the machine's transition function. Condition 3 means that after we have consumed the input string, the machine's current state is in a member of the accept state set. If an input satisfies these conditions, we say that M accepts the input string. And if we can generalize all of the strings that a machine accepts, we call that the machine's language. A language is considered a regular language if some finite automata can recognize it. That last sentence is rather important. Say I give you this definition of a language, and I want you to determine if it is a regular language. Let's answer this question by seeing if we can design a machine for it. First, picture yourself as a machine. You get to see the symbols in the string one by one. After each symbol, you decide if the string seen so far is a member of the language. You don't know when the end of the string is coming, so you will always have to have your answer on hand. As a DFA, you also have a finite memory, so you have to really know what is important. Those few things that you will need to remember about the input you have seen so far typically end up as these states inside of the machine. For our example, we need to remember if the number of ones we have seen is odd or even. Let's break these two key items into their own states, Q even and Q odd. Next, we see how the next symbol could affect each one of these states. If we are in a state with an even number of ones, receiving a 0 does nothing. The same is true if we receive a 0 while we have an odd number of ones. But if we have an even number of ones and we receive another, we need to transition into our odd state in order to remember where we are at. The same is true for the odd state. We want to transition into the even state if we receive a 1. Next up, we just want to know where to start. Well, if we haven't received anything, we will consider ourselves to be in the even state. So we mark that as an input arrow from the void. Finally, if we were reading the string and someone asks us if the string is valid, we want to immediately tell them yes or no. So we define our accept states. For this language, our only accept state is going to be Q odd. And with that, we have created a finite automata that recognizes the language. And because of this, we can say with certainty that this language is regular. Now, an exercise for you is to prove that the following language is regular by creating a DFA for it. Let's use this example string. We have 4 things that we as a machine need to remember about this input. 1, we haven't seen any part of the pattern yet. 2, we have just seen 1, 1. 3, we have just seen 2 or more ones. And 4, we have seen the entire pattern. These will become our 4 states. Then we start filling out transitions for each. We want to skip all zeros at first, so we just start and continue at state 0. Once we receive a 1, we slide into state 1. Here, once we receive a 1, we will slide into state 2. Here, if we receive a 0, we want to go back to where we have started because at this point we might as well not have ever seen any part of the pattern. In this state, we can receive any number of 1s because we are guaranteed to have seen at least 2 consecutive 1s back to back. And when we receive a 0, we transition to our last state. Here it doesn't matter if we receive a 1 or a 0 because we have already discovered our pattern in this string. These languages that we consider regular are part of a larger universe of languages that we can encounter. The set of regular languages can have mathematical operations performed on them like other mathematical sets. And in the next video, we will cover those operations. See you there.